All right. In this video, we are going to go over the answers to Worksheet 7.1. So here we go. Basically, we have some springs were used to make this graph right here. And the first question that we have is for each of the springs, determine the spring constant. So to do that, what we're going to be basically looking for, hang on a second. Is we're going to be looking for the slope. So, right, the spring constant, which is k, is going to be equal to the slope of each of these lines. So we are looking for, let's see here, let's start with spring 1. And to figure out the slope, just take any 2 points. So let's see here, we have this one right here, which starts at, it's like, is that 5, 6, 7, 8. So that starts at 5 and goes up to right here, looks like 15. So that's going to go up 10 and over, let's see here, it starts out at, where are we at here? This is a 1, and that is 3. So that's gone over 2. So K1 is equal to up 10 over 2. That's going to give you 5 newtons per meter. Let's take spring 2. And again, just pick 2 points on that. So I don't know, we'll pick that one, which looks like it's right there at 16. And let's see, where is it? And 2. So let's see here. We'll do this one a little bit differently. K2 is equal to, let's see here, we have, let's pick that one as well. That's 3. So that's 20 minus 16 on the top. 20, oh no, sorry. Oh, that's 24, sorry, 24. My bad. So it's going to go up 8, right? And over, that's going from 2, 3 to 2, or 2 to 3. So that's going over 1. Sorry, not 1. Again, that's going to give you 8 over 1, which gives you 8 newtons per meter as your answer. Okay. Let's see here. For B, it says, what is the force required when you stretch the spring 3 meters? There's 2 ways of doing that. One of the ways is to just basically draw the line straight up. So we can see that for spring 1, that's going to be 15 newtons. And for spring 2, that's going to be 24 newtons. We can double check that with the equation though. So let's just double check that. So the force for spring 1 would be equal to, right, I mean, it's kx, right? So that's just going to be 5 newtons times by 3 meters, which is going to give you 15 newtons, which is what we saw there. So that's good. And the other one, oh, I have that backward. Oh, no, that's correct. The other one, again, kx, and that's 8 times by 3, That's going to give you 24 newtons. So you could do it either way, right? You can use the equations like I just did, or you could just draw the line straight up and figure out what the forces are. Of course, that only will work if the you know uh, if the distance they give you is on the graph, right? They gave us 3 newtons or 3 meters. 3 meters is on the graph, but had they given us 10 meters, right, that wouldn't be on the graph anymore. Obviously, that wouldn't have worked, and you would have had to use the equation at that point. So. Okay, let's move on to number 2 here. So number 2 says the spring below has a spring constant of 10 newtons per meter. If the spring is pulled back 3 meters or 0.3 meters horizontally to the right and held motionless, what force does the spring exert on the block? So, um, real quick force diagram for the block. We would have force of gravity, normal force up. We have this force that is being applied to the right. Oh, hang on, sorry. That would be this guy right here. And then we would have the force of the spring, which is applied to the left there. It says, what force does the spring apply? In fact, I think in the hints, maybe I did this a little bit wrong. But, right, basically to calculate the force of the spring, that's just F is equal to Kx. It tells you that K is 10, tells you that X is 0.3. So that's going to be 3 newtons. And there you go. This one's a little bit different. So in this case, right, because this year we didn't get to the force of friction, this has been changed so that you're just given the force of friction. Um, so obviously, if we'd gotten to the force of friction, you would have had to calculate the force of friction, and you would have gotten 3.9 newtons. But this one's not too terribly different here. The basic idea here is that, well, actually, sorry, let's first draw the force diagram. We have the force of gravity, we have the normal force, we have the force of the spring, which is pulling to the left, and we have friction, which is going to resist that. And obviously, right, the further we push the block that way, right, we got, of course, the force of the spring is F equals Kx. So as you push it to the right, that's going to make X bigger, which is going to make the force of the spring bigger, right? As we push it to the right. And so what this question is basically asking, well, the one down here, what is the maximum distance that the spring can be stretched from equilibrium before the 1 kilogram box begins to slide? AKA at what delta x is the spring force equal to the maximum friction force. So this right here is the biggest that friction can be, right? If I didn't push it all the way to the right, then it wouldn't be more, it might, if I only pushed it a little ways, then I might not reach the full maximum 3.9 newtons. And so basically it's asking for the furthest I can push this, and the furthest the furthest I can stretch the spring out, and the furthest I can stretch the string out is when the force of the spring is also 3.9 newtons, right? When this force has reached the maximum force of friction, then that's the furthest I can stretch it, right? Because if I were to stretch it any more than that, then the force of the spring might be 4 newtons or 5 newtons, and at that point, then the box would begin to start to slide. So, so basically, we can do this all the way out, or you could just set Fs equal to 3.9. But basically, oops, hang on. And basically, right, FF is equal to Fs, right, when we've done at the maximum. And so we know that's 3.9 newtons. And the force of the spring is, right, Kx. We would like to know K, or we would like to know X. I believe it said that the spring constant is 20, so 3.9 is equal to 20 times by X divided by 20. and x is equal to 3.9, 1/5 just about, yep. 0.2 would be fine as well. Either or. Let's see here. So next, let's take a look at this one. This is kind of a weird situation, and I will tell you that the numbers on this are not super realistic. So let's take a look at, um, yeah. So let's first draw the force diagram. So as we read the situation, we'll draw the force diagram. So we have a large crate is being pulled to the right on level ground by a giant spring. Okay, so we got force to the right by a giant spring. Okay. Um, just put in the gravity and the normal force here. The spring is stretched a distance of 1.5 meters, and so that's going to give us, right, we could figure out kx, we got our 500 times by the 1.5, that's going to give you 750 newtons, so we know that that's 750 newtons. Okay, continuing on. A factory worker is pulling to the left on a rope tied to the crate, applying a steady force of 200 newtons. Okay, so they're pulling that way. That's the factory worker. I'm just going to label it as, I guess I could put a W there for the worker. That's 200 newtons. Okay, so we got a 700 Newton force to the right. We have, or 750 Newton force to the right. We have a 200 Newton force to the left. And then it says there's also friction, which is equal to 49 Newtons. So at this point, it doesn't tell us which way it's going to go, but remember that friction is always a resistance force. So as we look at this, right, this at this moment, the crate would go to the right, right? Because again, the 750 is bigger than the 200, so it's going to go to the right. And so that means free friction is going to resist that. So friction is going to be right there. It says find the resulting acceleration. So in order to do that, we just have to sum our forces. Again, it's going to accelerate, so we put an MA there, and that's going to give us the force of the spring minus the force of the worker minus the force of the friction. Again, those two are minus because they're to the left in the opposite direction that we're accelerating. Mass of the crate is 500 or 50. We have A is equal to, again, we know the force of the spring is 750. We just calculated that. The force of the worker is given as 200, and the force of friction is given as 49 newtons. So 50A, let's go ahead and find the net force here. So 750 minus 200, that's going to give you 550 minus 49. It's going to be 501. And then you divide by 50, and you're going to get just a little bit over 10, I believe. Oops. Yeah, basically 10, right? You could just make it 10, that's close enough. Let's see here. So there's your acceleration. Now, that's a really big acceleration. Like 10 newtons is, or 10 meters per second squared is a really big acceleration. So a couple things to say about that. In all likelihood, right, that's just a result of kind of us picking wrong, not so great of numbers. But two, it could also be that right when this crate is initially released, it's going to have a really big acceleration. But realize that that 750 is going to go down because the spring is going to become less and compressed or stretched less and less and less, and so therefore that number, that acceleration would go down fairly quickly as the crate began to move, just because the force of the spring would go down. Um, so yes, it is a really big acceleration, but realize that it would actually quickly decrease um, as we let this thing accelerate. So all right. Thank you for watching. I hope this was helpful. As always, let me know if you have any questions. And yeah, thank you.